This video is a collection of updates as they happened. Join the excitement as we learned more and more about Asteroid Bennu.
NASA's OSIRIS-REx has just arrived at the Bennu asteroid after 2 years of travelling through space. The mission has seemingly gone under the radar for most of the public, as it was not advertised nearly as much as the recent InSight landing on Mars. But I think you'll find this mission just as interesting, if not more so than the InSight lander. So what will it do there? What are its mission goals? And why is it there in the first place? I'm Alex McColgan and you're watching Astrum, and together we will go through everything you could want to know about the OSIRIS-REx mission. Let's start from the beginning. OSIRIS-REx is part of the New Frontiers NASA program, along with Juno and New Horizons, which means it's part of a high pedigree if you've been following those other missions. It launched in September 2016 and arrived near Bennu on the 3rd of December 2018, where it has begun imaging the surface. Although Bennu is a near-Earth asteroid, it still took a long time to get there. This is because Bennu does not orbit along the plane of Earth, and its gravity is incredibly weak, which means OSIRIS-REx had to slow down a lot, or it would have simply overshot its mark. Interestingly, the OSIRIS team had a pretty good idea of what Bennu would look like long before OSIRIS-REx even launched. This was because they used radar data to simulate what it would look like. As OSIRIS-REx approached Bennu, the images it sent back were progressively more and more clear, and the OSIRIS team saw that their predictions were surprisingly accurate. Eventually, it got to within 20 kilometers of the asteroid, and what it saw was amazing. This is an actual time-lapse of the Bennu asteroid as seen by OSIRIS-REx. If you compare the simulation to the actual photographs, it's amazing how accurate their predictions were. As you can see, it's not a particularly smooth asteroid, covered with rough regolith all over the surface. It reminds me a lot of the surface of another asteroid that was visited by the JAXA probe Hayabusa, the asteroid Itokawa, which was more like a clump of rubble than anything else. Bennu itself is about 500 meters in diameter and has this weird spinning top-like shape. This could be because Bennu has a low gravity but a fast rotation, so regolith has accumulated there as it span. Bennu is a carbonaceous asteroid, but in the less common B-type classification. This puts it in the same category as the third biggest asteroid in the solar system, Pallas, and Bennu could even be the ejector from an impact early in Pallas's life. B-type carbonaceous also means it has a very low albedo, or that it doesn't reflect a lot of sunlight. Other tests show it could be an even rarer F-type asteroid instead, and as such could have been part of the Polana family of asteroid, meaning it came from the 55-kilometer big asteroid Polana. In either case, its orbit has changed significantly through various processes and interactions to bring it closer to the orbit of Earth. Speaking of its orbit, it is one of the most likely asteroids we know of that could impact Earth. Although based off the most recent estimate in 2014, this won't happen until 2175, and even then, there's only a 1 in 2,700 chance of doing so. Before OSIRIS-REx will go in orbit around Bennu, it first needs to see if there are any small moons or debris around the asteroid, so there isn't any risk of a collision. It will do this by going back and forth a few times around the asteroid, also getting a sense of the gravity of an object so small. Once the prime orbit has been located, OSIRIS-REx will orbit roughly 1.4 kilometers above its surface, mapping out the surface of Bennu in detail, looking for differences in minerals across the surface of the asteroid. Interestingly, this means that Bennu will be the smallest world ever to be orbited by a spacecraft. This will last for about 1 year, and what scientists are looking for is the sampling site. You see, unlike most robotic NASA missions that don't return to Earth, OSIRIS-REx will, hopefully carrying samples of the asteroid with it. OSIRIS-REx is unique in that it is a sample return mission, the first time NASA will be doing this with an asteroid. Although it should be noted that JAXA has done this before with the Hayabusa mission, and are currently in the process of doing it again with Hayabusa 2. Once the sampling site has been chosen in mid-2020, OSIRIS-REx will drift extremely slowly towards Bennu to land. This slow speed is to avoid the use of thrusters as much as possible. If the thrusters are used close to the surface, the gas from them could contaminate the samples. The solar arrays will fold into a Y shape upon descent to avoid dust settling on the panels after the impact with the surface, and to provide more ground clearance should the spacecraft tip over. However, the force of the impact should be dissipated by a spring on the arm of OSIRIS-REx. Once it is landed, it will fire a burst of nitrogen gas at the ground, blowing particles up to 2 centimeters into the sample collection chamber in the arm. After 5 seconds, the sample collector will close and the spacecraft will back away from the asteroid. Scientists are hoping for about 60 grams of material. It will find out how much mass it has in a really clever way. It will do a spin to see the change in inertia with this added weight. If it wasn't able to collect enough samples, it will go in for another try. Should everything go well at this point, the container will be stowed by a robotic arm. By 2023, OSIRIS-REx will eject the sample capsule back towards Earth, where it will be picked up by scientists in the Utah desert. This is when the sample study part of the mission will begin. OSIRIS-REx will continue to orbit the Sun long into the future. But why asteroids? Apart from the curiosity factor, is there anything that actually makes asteroids special? Well, asteroids are remnants of some of the oldest objects in our solar system. They were there when everything was in the process of forming around the Sun. To this end, asteroids can tell us a lot about the formation of the solar system. They are the building blocks of planets, and also potentially life. Asteroids could be the source of water on Earth, and they mysteriously contain organic materials like hydrocarbons and amino acids. Actual uncontaminated samples of asteroids will provide insight into this, enabling us to have a better understanding of the universe we live in. So hopefully this mission will be as successful as its other New Frontier cousins.
OSIRIS-REx has been in orbit around the asteroid Bennu for around a year now. Bennu is the smallest object ever orbited, and as a result, OSIRIS-REx orbits only several hundred meters above its surface. Being so close to the asteroid means it can examine its entirety in minute detail. So what has it discovered and seen so far? And what does the mission still have to do? I'm Alex McColgan and you're watching Astrum, and together we will explore the surface of Bennu, talk about any special findings that have come up so far, and investigate what's coming up next for this special mission. As I mentioned, one of the most unique things about this mission is the fact that OSIRIS-REx is orbiting Bennu, which is only 500 meters wide. A 500 meter wide object barely has any gravity at all, which means one orbit of Bennu takes 62 hours at an altitude of 1.75 kilometers. However, orbiting Bennu was necessary to map its surface accurately. As the spacecraft orbits and the asteroid rotates, OSIRIS-REx is scanning the surface, creating the highest resolution map of any celestial body to date. This detailed examination is to find the best landing site for OSIRIS-REx, which is actually a sample return mission. Scientists want to retrieve 60 grams from the surface of Bennu and return it back to Earth in pristine condition. While there are a lot of meteorites that land on the surface of Earth, and we have many samples, these meteorites pass through our atmosphere, heating up to incredible temperatures, which alters the delicate materials in the meteorite. Upon impact, they are also then exposed to the surface of Earth, making it hard for scientists to distinguish what was there from before and after the impact. A sample directly from an asteroid protected in a box from contamination which occurs during the re-entry process, can give a much greater insight to the nature of asteroids than anything we have observed before. With this sample, scientists will be able to search for organic compounds like amino acids, hydrated materials like clays, and other substances that would otherwise be hard to detect. But has OSIRIS-REx found anything interesting during its preliminary scans? OSIRIS-REx isn't just taking photos of the asteroid, but it is also mapping the global properties, chemistry, and mineralogy of this primitive carbonaceous asteroid to characterize its geologic and dynamic history, to provide context for the return samples. It's doing this to help pick the best site for the sample return part of the mission. Scientists are looking for the most geologically interesting site that can provide the most interesting sample. Spectroscopic surveys have already revealed that there are hydrated materials, or in other words, clays on the surface of Bennu. This is significant. Clays contain water, and Bennu was not the type of body where scientists expected to find traces of water. Scientists are still of the belief that a body as small as Bennu could never have held its own water, but what this does imply is that liquid water was likely present on the body Bennu would have originated from, and all that remains of it is what has been locked away in these clays. Scientists had a rough idea of what Bennu looked like before OSIRIS-REx even arrived, thanks to radar imaging from ground-based telescopes. However, what they didn't expect is just how much the surface is covered with large boulders. Many asteroids have been described as rubble piles in the past, but I don't think anyone was expecting it at this scale. Just to give you a sense of scale, the largest boulder on the surface is 20 meters high and about the size of a football field. Other boulders you see here are about the size of a horse. This makes picking a landing site a little tricky when ideally you are looking for a patch roughly 25 meters in diameter containing particles no bigger than a centimeter, so your sample collector can retrieve a sample safely. However, 4 smaller landing sites were eventually chosen, named Osprey, Kingfisher, Nightingale, and Sandpiper. Even though they are smaller sites than originally hoped for, the sites are relatively free from boulders. Scientists have had to adjust and refine their plans to make sure OSIRIS-REx will hit its mark, as the difficulty of the maneuver is exasperated by the small size of the landing sites, which are no bigger than a few car parking spaces, with large and dangerous boulders surrounding them. It won't be long before the final sample site is picked, and within a few months of that, mission controllers will attempt the sample collection. All being well, they'll be successful on their first attempt, but they do have the fuel to try again should they not get anything the first time, and if they don't crash. Considering Bennu is seemingly an inactive pile of rocks floating in space, Bennu also surprised scientists greatly when OSIRIS-REx spotted some dynamic activity on the asteroid. Occasional ejection events were spotted, where some material was flung away into space. Some of these particles were even captured in orbit around the asteroid for a few orbits, before eventually returning to the asteroid's surface. This is likely due to the fast rotation of the asteroid, and OSIRIS-REx has already been able to detect that this rotation is speeding up very gradually due to the Yorp effect. This effect is caused by the slight pushing effect from solar radiation acting on an irregularly shaped object, causing it to rotate faster over very long periods of time. The speed of the rotation can already be seen due to the buildup of rocks along the equator through centrifugal forces. If the rotation continues to speed up, then the asteroid might eventually disintegrate altogether when centrifugal forces overcome the gravity of the asteroid. This can already be seen in small events like the one I showed you before. So, in short, Bennu had a lot of surprises waiting for scientists when OSIRIS-REx arrived. It was a lot more lumpy than expected, with giant boulders comprising almost the entirety of the surface. It contains clays and other hydrated minerals, and dynamic activity originating from Bennu was witnessed up close. We still have the sample collection part of the mission to go, and I can't wait to see what else Bennu has in store for us. When it comes to astronomy, the approach of poke it with a stick is usually not a very viable option. You cannot poke stars with a stick, and not much can normally be learned by poking planets. However, if your stick is actually a high-tech sample collection device, and you target a cosmological time capsule composed of loose regolith and dust, suddenly we have the setting for the largest and most scientifically advanced stick poking in human history. And with the OSIRIS-REx spacecraft's mission to the Bennu asteroid, that's exactly what happened. I'm Alex McColgan and you're watching Astrum, and today we continue with our third look at the OSIRIS-REx program. In this video, we explore the moment of truth, the culmination of a journey that spanned 4 years, the first time in history a US spacecraft poked an asteroid. If you watched my other videos on this topic, you will remember that the OSIRIS-REx, or the Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer, is a NASA-developed spacecraft that was launched in 2016 with the mission of collecting and then bringing home to Earth a sample from the near-Earth asteroid known as 101955 Bennu. This mission is an important one, as Bennu is an extremely old asteroid. It is thought to have been around since the birth of the solar system, and as such is a treasure trove of information about the solar system's formation, and maybe even the origins of life. However, while missions have photographed asteroids before, and have even collected stardust from the tails of comets, this was the first time a US spacecraft would have ever traveled to an asteroid to physically collect a sample from its surface. NASA's goal was to collect a 60-gram sample of regolith and dust from Bennu's surface. It would do that by entering Bennu's orbit and slowly descending. It would be careful not to disturb or contaminate the asteroid's surface by using its thrusters, but would drift gently down, extending its long touch-and-go sample acquisition mechanism, or TAG-SAM, as it did so. Then, at the moment it touched the surface of the asteroid, it would release a burst of nitrogen gas from its arm, kicking up dust and materials, which would be captured in its sampler. OSIRIS-REx would then return home with its sample. However, that mission was not as simple as it may sound. Bennu is a relatively small asteroid, only about 490 meters in diameter, which meant that there was very little gravity. While scientists had previously mapped out the rough shape of Bennu to a surprisingly high degree of accuracy using radar imaging, this low gravity had led them to believe that Bennu would be made of relatively fine materials. This was not the case. Bennu was covered in large boulders, some of which were 58 meters across. As such, there were limited places where OSIRIS-REx would be able to touch down to collect its sample. And so, OSIRIS-REx spent over a year, 505 days, circling Bennu and mapping out its surface, choosing the best location for its system-spanning pogo stick hop. After careful deliberation, NASA had decided on potentially 4 sites for the sample collection: Osprey, Kingfisher, Nightingale, and Sandpiper. You might notice a bird theme here. Bennu itself was named as the result of a contest run by the University of Arizona, the Planetary Society, and the Linear Project in 2012. In it, more than 8,000 students submitted name ideas. The winner was a 3rd grade student who wanted to name the asteroid after the Egyptian mythological bird Bennu, because he thought that the OSIRIS-REx's TAG-SAM arm looked like the graceful extension of a heron's neck, just like the Egyptian god Bennu, meaning it was named after the craft visiting it rather than the shape of the asteroid itself. NASA seems to have kept with this bird-like naming convention. In the end, NASA chose the Nightingale site for Osiris's landing. The site was set in a crater that seemed to be relatively young and clear of rocks, which came with numerous benefits. Not only would landing be easier, but the recently exposed material beneath Bennu's surface would likely be an accurate reflection of the asteroid's internal workings. With the site selected, Osiris began its slow descent. However, it did not rush in with a single try. Instead, it did practice runs. The first took place on the 15th of April 2020. OSIRIS-REx approached the asteroid to a distance of 65 meters before activating its thrusters and rising again. Everything worked perfectly, and its thrusters worked just as intended. Satisfied with this run, scientists sent it in again. On the 11th of August, OSIRIS-REx approached at a distance of 40 meters before once again rising, slowly darting forwards and backwards, but drawing ever closer. And on the 20th of October, this heron look-alike went in to strike. Using onboard computer systems to plan its trajectory and perform its operations, as the lag time for signals from Earth rendered real-time remote control of the spacecraft impossible, OSIRIS slowly reached out to touch the surface of the asteroid. It raised its solar panels in a Y shape to keep them out of the way and protect them from any loose dust that was about to go flying. It reached out its arm to land. It touched the surface, and then, surprisingly, it kept going. When I think of the surface of asteroids and comets, I imagine them as firm and hard enough to stand on, as you might see in films such as Armageddon. But the truth is that, particularly for small asteroids like Bennu, their low gravity means that their mass is only loosely held together. What looks like a stable surface is actually loosely held material interspersed with pockets of nothingness, gaps that mean Bennu is so easy to sink into, if you stepped on it, you'd likely vanish inside of it. Like stepping into foam, OSIRIS-REx's arm sank almost half a meter into the surface of Bennu before the thrusters arrested its fall. Furiously activating its nitrogen gas burst, OSIRIS blasted a hole in the side of the asteroid. What was expected to kick up a little regolith and dust displaced over 6 tons of loose rock, as all that material, so loosely held together under Bennu's tiny gravity, was catapulted in all directions. OSIRIS-REx's thrusters went into overdrive, burning the most they had ever burned on this trip to pull them away from the expanding cloud of dust. Of course, this was all pre-programmed. NASA had planned for this, although perhaps not to this extreme. OSIRIS-REx had just made a new massive crater in Bennu. Upon getting away from the asteroid surface, OSIRIS-REx checked its haul. It had hoped for 60 grams of material. Instead, it found it had collected somewhere between 400 grams and over 1 kilogram of material. So much material had been collected that a rock got stuck in the flap that closed the sampler's head, causing some small amount of the material to get lost. However, OSIRIS-REx succeeded in transferring the sampler head to a sealed container built into it. Its mission had been a huge success. For a time, OSIRIS-REx stayed watching, flying over the asteroid to image it and see the outcome of what it had done. The surface of Bennu was different now. Even larger materials had moved far. Just look at how far this boulder was thrown, around 12 meters across Bennu's surface. However, OSIRIS-REx couldn't linger forever. Its sample needed to get back to Earth, and so, after performing one last flyby on April 7th, 2021, it began a long journey home. And there we have it. Right now, as of the release of this video, OSIRIS-REx is making its way back through the void of space. It is thought that it will arrive back around Earth by September 2023. Once it reaches Earth's orbit, it will release its sample, which will fall through our atmosphere to land in the Utah desert, where it will be collected and examined. This will mark the culmination of an incredible scientific exercise, collecting a sample of an asteroid and returning it back in pristine condition to Earth. But as for OSIRIS-REx itself, this mission was only the beginning. Having captured a sample of Bennu, this Egyptian heron will be off to slay a new beast, Apophis, the Egyptian serpent of chaos, destroyer of light and order. Or more accurately, the Apophis asteroid, a 370-meter diameter asteroid that is believed to be passing within 50,000 kilometers of Earth in 2029. Let's hope that the asteroid does not behave in a way that's too in keeping with its Egyptian namesake. Either way, OSIRIS will be heading off to investigate it, once again using its thrusters to kick up material from the asteroid's surface for analysis. To reflect this extension of the mission, OSIRIS has been given a new name. No longer is it OSIRIS-REx, it is now Osiris-Apex Explorer, or Osiris-Apex. With a name like that, perhaps its greatest discoveries are yet to come. For the first time in the US's history, the NASA OSIRIS-REx mission was able to collect a pristine 4.5 billion-year-old sample from the surface of an asteroid. And in May 2021, the spacecraft set off on its 1.9 billion kilometer return trip to bring the asteroid dust and rocks back to Earth. 2 years and 4 months later, the sample return capsule re-entered Earth's atmosphere in September 2023, traveling at more than 44,000 kilometers per hour, marking an extraordinary achievement in space exploration. Like an ancient time capsule carrying materials from our early solar system, the sample from Asteroid Bennu is allowing scientists to uncover evidence about the asteroid's origins from a possible water world and expand on the history of our solar system. What secrets have been revealed through Bennu's rocks and dust? How might this change our understanding of our solar system and the origins of life? And what's next for the OSIRIS spacecraft? I'm Alex McColgan and you're watching Astrum. Join me today as we recount the historic return of the sample capsule from the OSIRIS-REx mission and delve into the fascinating things we've learned from it so far. In previous videos of OSIRIS-REx, or Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer, I talked about its launch back in September of 2016 and its incredible journey to the near-Earth asteroid known as Bennu. If you'd like to learn more about the mission, from breathtaking high-resolution images of the asteroid's surface to the moment of truth when, in October 2020, the spacecraft touched down and collected material from Bennu, I encourage you to explore my other videos. This video will focus on the return of the sample capsule and the project's findings. After 7 years of anticipation, space travel, and data and sample collection, OSIRIS-REx returned to Earth. Or rather, it passed by Earth in order to return its special cargo. As the spacecraft reached a point about 100,000 kilometers away from our planet, it jettisoned the sample return capsule towards the atmosphere on the 24th of September 2023. Then, OSIRIS-REx fired its thrusters to avoid itself colliding with Earth and began a new mission, which we'll talk about later. This calculated maneuver had to happen within a narrow window of time and at just the right angle in order for the return capsule to hit its target of about 600 square kilometers in a Utah desert in the western United States. That's roughly the size of the city of Chicago, or the size of the Isle of Man. As the capsule hurtled towards Earth at a top speed of 43,000 kilometers per hour, it became the second fastest human-made object to enter Earth's atmosphere, only 3,000 kilometers per hour slower than NASA's Stardust return capsule, and enduring an astounding 32 g-forces, or 32 times the acceleration due to Earth's gravity. To put this into context, standing on Earth you receive 1 g, and a typical person would lose consciousness with about 4 to 5 vertical g's. Today's astronauts experience about 3 g's during launch, and for very short periods of time, a fighter pilot may be able to withstand up to 8 or 9 g's with the help of a specialized suit and training to increase their tolerance. It's almost unfathomable to imagine the 32 g's the return capsule was built to withstand. The scalding hot capsule streaked through the atmosphere, reaching peak temperatures of around 2,700 degrees Celsius, which is about half as hot as the surface of the Sun, allowing ground-based infrared trackers to monitor its progress. Inside the capsule, the 120-gram sample from Asteroid Bennu was protected from these extreme temperatures thanks to an advanced thermal protection system called PICA, or Phenolic Impregnated Carbon Ablator, which removed more than 99% of the kinetic energy of the vehicle and kept the sample below 75 degrees Celsius. Pika is a type of ablative heat shield which works by using a protective layer on the outside of a spacecraft to safeguard it during re-entry. Because the spacecraft experiences extreme friction on its way down through the atmosphere, it generates immense heat. As the temperature of the shield heats up, it burns away its outer layer in a process called ablation. During this process, the heat shield melts and vaporizes, and those gases carry the heat away from the spacecraft. This sacrificial shield prevents heat from reaching the interior of the return capsule, keeping the asteroid sample cool and safe. A couple of minutes after re-entry, the capsule decelerated enough to release the first of 2 parachutes, which helped to stabilize it for the remainder of its trip to the surface. About 16 kilometers from the ground, radars were able to lock onto the capsule's location and track it to within about 10 meters of where it would eventually land. And for the final 1.5 kilometers of descent, a second parachute was deployed to soften the landing to a leisurely speed of 18 kilometers per hour, or about the average speed of a cyclist on flat ground. From the moment it pierced Earth's atmosphere to when the capsule gently touched down in the rugged desert landscape of Utah, it took just 10 minutes. After years of planning, months of special training, and several rehearsals, the NASA recovery team moved in by helicopter to secure the return capsule and its contents. To ensure the sample was not exposed to Earth's environment, the capsule remained closed until after it had been moved to a clean room and decontaminated. But opening the sample canister didn't quite go according to plan. Within a couple of weeks, scientists at NASA's Johnson Space Center in Houston, Texas, were able to open the outer lid, revealing 70 grams of dark grey rocks and dust outside of the sample canister. While this bonus material from Bennu was able to be analysed and used in scientific research, it wasn't as pristine as the material held inside the inner sample canister. However, it would take months and the invention of a new tool before the curation team at the Johnson Space Center was able to open the main sample canister to reveal this pristine material. The mission was meticulously planned, so why did they need to invent a new tool just to open the canister? And why did it take so long? Well, for one thing, the bonus material slowed down the process of getting into the inner canister because all of that extra material had to be carefully removed, catalogued and stored. And while it may not sound like a lot, the 70 grams of the bonus material alone was 10 grams more than the mission's original target sample size. Another reason this took a long time is because all of these tedious tasks had to be done inside of a nitrogen purged glove box, an enclosed box with built-in gloves that is constantly flooded with a flow of neutral nitrogen gas to make sure the sample does not react with other gases in Earth's atmosphere like oxygen or water vapor. While use of this clean environment was necessary to make sure the sample remained uncontaminated, the glove box made a set of already tedious tasks even more difficult. But the main slowdown came during disassembly of the canister, called the touch and go sample acquisition mechanism, when 2 of the 35 fasteners holding it shut could not be removed with existing tools. The 2 problem screws had been infiltrated by dust from Bennu, essentially causing the threads to be stripped. Imagine having successfully retrieved this capsule after its arduous journey to Bennu and back, just to not be able to actually open it. But NASA engineers wouldn't be NASA engineers if they didn't immediately set to work to invent what was needed to crack this nut open. Because the samples needed to be protected from any contamination, the new screwdriver-like tool with custom fabricated bits made from a specific grade of surgical, non-magnetic stainless steel had to be designed, fabricated and tested before it could be introduced into the pristine glove box. But all of this time and effort paid off. 3.5 months after the return capsule touched down on Earth, the curation team was finally able to access the material inside the canister using these new tools. Another 51 grams of pristine Bennu material was revealed, and when combined with the bonus rocks and dust already collected, the total amounted to more than twice what the mission had aimed to bring back to Earth. The material was then catalogued and divided into smaller samples. At least 70% of the material will be preserved in its pristine condition for future generations to have the opportunity to study, and from the remaining material, more than 200 scientists at labs around the world will have the chance to study pieces of Asteroid Bennu. So what's so special about this handful of space dirt? Well, just imagine being able to study a piece of our solar system's past, a sample packed with clues about the origins of life and the early solar system. What awesome stories could an ancient relic like Bennu tell? Just over a week after recovering the return capsule from OSIRIS-REx, scientists got their first look at the bonus asteroid soil sample, called regolith. While Bennu might have broken off from a much larger asteroid 1 or 2 billion years ago, its present-day chemistry and mineralogy were already set in stone, so to speak, more than 4.5 billion years ago. Since its composition has remained relatively unchanged, Bennu contains the primordial ingredients that were present before our planets existed. The sample from Bennu contains what are called presolar grains, which are microscopic crystals that condensed before our Sun came to be. Depending on the composition of these presolar grains, we can get an idea for the types of stars that existed before our own solar system formed. The higher the mass of a star, the heavier elements it will be able to fuse together. For example, small and intermediate mass stars burn by fusing light elements like hydrogen into helium, and may eventually fuse heavier elements such as carbon and nitrogen. Large mass stars can fuse together even heavier elements like silicon and iron. Importantly, these large mass stars can end their life in a supernova explosion, creating elements even heavier than iron. Because these elements from stellar fusion get spread across the universe and recycled to form new stars, asteroids, and planets, we can learn about the ancient building blocks of our own solar system by looking at these pre-solar grains. A cosmochemist at the University of Arizona and member of the OSIRIS-REx team said that initial analysis of these pre-solar grains showed evidence of small and medium-sized stars, but also of supernovae. This supports the idea that our solar system was enriched by a range of different sized stars long before our solar system formed. Initial analysis of the asteroid sample revealed a dust rich in carbon, nitrogen, and organic compounds. These ingredients are essential building blocks to life as we know it. NASA's OSIRIS-REx science team also found evidence of water in Bennu's past, in the form of water-bearing clay minerals in the sample. These clay minerals confirmed what scientists had previously observed in spectroscopic surveys of Bennu, as we mentioned in a previous video. They indicated that Bennu may have originated from a larger body that once contained water. But how do these ingredients of life end up on a seemingly barren asteroid? And why is there evidence of water? As it turns out, these essential ingredients of life are abundant throughout the universe. Planetary scientists and astronomers have identified organic compounds across our solar system, throughout the Milky Way galaxy, and even in interstellar space. We find these compounds in asteroids and meteorites, on moons, in nebulae across the galaxy, and beyond. All it takes for these simple building blocks of life to form is a combination of oxygen, carbon, and nitrogen, which are the third, fourth, and fifth most abundant elements in the universe by number of atoms respectively. These elements are created inside of stars, and remnants from those ancient stars are spread across the universe. We are made of star stuff, and from what we've learned, the stuff of life is abundant. But the presence of amino acids and other organic compounds doesn't mean that life ever arose in those places. In fact, with no atmosphere and temperatures ranging from a frigid -73 degrees Celsius up to a scorching 116 degrees Celsius, Bennu is not a very hospitable place for life to have developed. Rather, the presence of organic compounds means the building blocks of life seem to be abundant throughout the universe, and asteroid Bennu is further proof. Astronomer Dr. Carl Sagan once compared the emergence of life to a musical composition. The organic compounds on Bennu are like a collection of unorganized musical notes that do not yet create the music itself. Still, finding these molecules in such a pristine sample from Bennu is exciting, as these minerals could offer clues about the chemical reactions that predate biology. More intriguingly, perhaps, is that planetary scientists like Sarah Russell at London's Natural History Museum and an OSIRIS-REx team member said the sample is dominated by hydrated minerals, suggesting that Bennu may have once been part of a larger body that harbored water. The sample was packed with evidence of dynamic transformations that occurred over time in the presence of water, like clay minerals or salts left after water evaporates. It contained a mineral called serpentine, which mirrors a type of rock that we find at mid-ocean ridges on Earth. These mid-ocean ridges are where molten material rises up from within Earth's mantle and encounters water, creating new crust along the ocean floor. Bennu's regolith also harbored pyrrhotite, an iron sulfide material that can form near hydrothermal vents on Earth. And even more surprisingly, the OSIRIS-REx team found phosphates in the sample, an essential component of DNA and, in turn, for life on Earth. The presence of these water-soluble phosphates indicates that billions of years ago, Bennu may have been part of a larger, water-soaked mud ball, or even a world with an active geology and an abundance of organic compounds. While there isn't enough evidence yet to conclude that Bennu came from an ancient water world, Harold Connolly, a geologist at Rowan University and OSIRIS-REx mission sample scientist, said that evidence of warm water over time in the sample does indicate that Bennu's parent body was at least 10 kilometers wide or even larger. Although more research is happening in order to further study these indications, it's incredible to imagine that Bennu may have originated from a much larger asteroid or a protoplanet that shared some important characteristics with the primitive Earth, or with some of the icy, ocean-covered moons across the solar system like Enceladus or Europa. So what else can we learn from the Bennu samples, and what comes next for the OSIRIS-REx spacecraft? The data and samples from OSIRIS-REx will keep scientists busy for years to come, as planetary scientists, geologists, astrobiologists, chemists, and interdisciplinary research teams around the world continue to study this one-of-a-kind sample from Bennu. And while we have a pretty good understanding of how the solar system and our planets formed, this is giving us the opportunity to calibrate, confirm, and adjust our current knowledge, and to explore the answers to new questions that are only possible because of the OSIRIS-REx mission. Did the stellar nebula of dust and gas that went to form our sun and planets all come from just one ancient star? Or did it come from multiple generations of stars of different star types? Where did Bennu's parent body form? And what materials was it made of? And during Earth's formation and early existence, did some of its water or organic compounds come from asteroids? These are just a few of the long list of questions that scientists are hoping to shed light on in the coming years with the help from the Bennu sample. As for the spacecraft's missions, they don't end there. About 20 minutes after releasing the Bennu sample capsule above Earth's atmosphere, the OSIRIS-REx spacecraft fired its engines to send it on a new trajectory and a new mission. Now renamed the Osiris-Apex Explorer, or Osiris-Apex, for its new target, the spacecraft will travel to and explore a different type of asteroid, this one named Apophis, and it will reach in 2029. Starting in June 2029, it will begin an 18-month campaign to map the asteroid's surface, analyze its chemical makeup, and to observe any changes that happen to Apophis during a near-Earth encounter. Finally, the spacecraft will repeat one of its most impressive maneuvers from the mission to Bennu by dipping within 16 feet of the asteroid's surface and firing its thrusters to stir up rocks and dust. Unlike with Bennu, the Osiris-Apex mission will not collect a sample from Apophis, but this move will give us a chance to look at the material that lies below the surface of another near-Earth asteroid. You might have also heard that Asteroid Bennu has a chance of colliding with the Earth in 160 years, although this is a very slight possibility of less than 1 in 1,700, so we most likely have nothing to worry about. But in addition to the scientific investigations centered around the return sample, the OSIRIS-REx mission to Bennu also gave scientists precision tracking information that will significantly reduce the uncertainties about Bennu's future orbit. The initial analysis of Bennu's samples have exceeded our expectations in several ways, and I can't wait to see what other secrets Bennu and Apophis will reveal. Thanks for watching. We are now very close to our end goal of 1,000 astronauts on Patreon, and I can't thank you enough for having answered the call. The closer we get, the more it's looking like I'll be able to expand our content here and bring back Astrum Answers. So submit your video suggestions and questions over on Patreon. If you'd like to become an astronaut, you can join the Patreon with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.